After making the data into a data frame, we can get an overview of the data and some basic information on the shape of the data frame as well as its missing values. In total, there are 20 columns which are specified here. In this analysis, the ID column, which is a unique identifier of individual patients, is dropped, as it is irrelevant to the analysis. Now, the analysis defines the type of features and target variables with this block of codes. The codes separate features into quantitative and categorical and define stage as the target variable. Next, the analysis checks the number of missing or null values, as well as any duplicates. A statistical summary of each quantitative column is also displayed here. So to handle missing values, the analysis replaces all missing values in quantitative features by the value 0. And it also replaces missing values in certain categorical features by string 0. This way, we don't have to lose all the rows containing null values. Now, since the prediction outcome should be either cirrhosis or no cirrhosis, we need to replace the 4 values in stage by only 2 values, where 1 means cirrhosis and 0 means no cirrhosis. What this block of code does is that it replaces stage 4 with 1, and the rest of the 3 stages as 0. Next, the analysis ensures that all columns in quantitative features are numerical values. The analysis also checks for skewness, and after identifying columns with skewness greater than 1, it uses a log transformation to reduce the impact of large numbers and make the distribution closer to normal. This is because many machine learning models perform better when the input feature have distributions closer to normal. Now, the analysis also handles outliers by defining the upper limit as the median plus 2 times the interquartile and the lower limit as the median minus 2 times interquartile. Outliers are the values that are lower than the lower limit or higher than the upper limit. The identified outliers are then Winsorized, which means that they're replaced by less extreme values. Next, this line of code here encodes categorical values into dummy variables, which is a format that is suitable for machine learning models. For example, the column drug has 2 values, D-penicillamine and placebo. This line of code creates 2 columns, which are drug underscore D-penicillamine and drug underscore placebo. This analysis also creates a correlation heat map here to visualize relationships between numerical variables. So to set up for modeling, the data is first split into training and testing sets. The code specifies that the training set is 80% of the data set and testing set is 20% of the data set. Additionally, this analysis standardized features, which means that it transforms the data to have a mean of 0 and a standard deviation of 1 for each feature. It also balances the data with SMOT. which handles imbalanced data sets by generating synthetic samples for the minority class. This prevents the model from being biased towards the majority class. It is also worthy to note that SMOTE here does not affect testing sets, so it avoids data leakage. Next, the analysis fits the training data into a decision tree classifier. It then uses the trained pipeline to predict the target variable for the test set. This classifier yields an accuracy score of 0.64 and a confusion matrix with 36 true negatives, 13 true false negatives, 17 false positives, and 18 true positives. Next, the analysis moves to utilize PyCaret. Because PyCaret allows users to compare multiple machine learning models at the same time. After comparing the models, it creates a model with the best model found in the comparison. It then makes predictions on the test data, which with the finalized tuned model. This analysis chooses a decision tree model. It is suitable for the data set because first, the outcome that we are trying to predict is binary. Either the patient will have cirrhosis or will not have cirrhosis. Potentially relevant features include both quantitative and categorical data, and they are nonlinear with the target variable. We know that the decision tree model can handle nonlinear and mixed data, and it also takes into account feature interaction. Also, the decision tree model can be easily interpreted, which makes it very practical because we need to explain the results to non-technical healthcare providers. Decision trees also provide a natural mechanism for evaluating feature importance. By examining the splits that lead to the most significant reduction in impurity, we can determine which features are the most important for predicting the target. However, it should be noted that the decision tree model is prone to overfitting, which leads to the discussion of bias variance trade-off. A shallow tree can have high bias and low variance, which makes it underfitting the data. On the other hand, a deep tree will have low bias but high variance, overfitting the data. The ideal model should have a balance where both bias and variance are minimized. One strategy used in this analysis to manage the bias variance trade-off is cross-validation. Cross-validation evaluates the generalization performance of a model, ensuring that it performs well on unseen data. The model is evaluated on multiple subsets of the data, helping to reduce the likelihood of overfitting. It also provides more reliable performance metrics. Also, cross-validation provides a more stable and reliable estimate of the model's performance across different parts of the data set. It also allows for better model selection and hyperparameter tuning. Now let's take a closer look at the results. For the simple decision tree model, it has an accuracy of 0.64, and the cross-validation score is 0.67. Using PyCaret, we can see that the best model here is Extra Trees Classifier. It has the highest accuracy, about 0.76, which is the proportion of correct predictions. It also has the highest precision, which is the proportion of positive predictions that are actually correct. However, this model does not have a high recall or sensitivity, which means the proportion of actual positives correctly identified by the model. It does not have a very high area under the curve either, which indicates better performance at distinguishing between classes. Also, it should be noted that after tuning, we found the original model actually has a better performance. This is very likely an example of overfitting. The final result, which somehow does not show in this interactive chart, should give us an idea of the important features in predicting cirrhosis. This is valuable for real-world applications because with sensitivity of 60%, which means that 60% of actual positives can be correctly identified, doctors can now start preventative treatments for those that are riskier of getting the disease.